Calgary. No, I'm being recorded. Okay, good. My name is Roger Bernard, and I'm with the Novel Hydrocarbon Extraction Group here at CRIN. So just for the people here, the men's washrooms are to my left. Women's washrooms are to the right, and you need a key. And there's no fire alarms today, to my knowledge, but if we do hear one, the fire exit's over here to my right, and or I guess to your left. There we go. And we are online, so there is a virtual audience. They'll be asked to submit their questions by chat, and we'll have questions starting at 1:15 to 1:30. So if you can save your questions until then, and then we'll have networking afterwards. So there is time, another half an hour afterwards. So we have this space. So please feel free to stick around and grab your cookies afterwards or what have you. Let me see, any other logistics? Oh yes, when you're asking your questions here in the audience, if you could put your hand up and you state your name and affiliation, and we'll come over and give you a microphone to ask the questions. Let's see if I have anything else here. I think I'm good. Did I cover everything? Good. Again, thanks everyone. It's January 2026. Unbelievable, and what a year. A lot of changes. And the novel hydrocarbon extraction theme, we're seeking innovative technologies that advance extraction while significantly reducing environmental impact. Technology should deliver step change improvements in emissions, reduction, water use, and operational efficiency, and enhanced oil recovery fits that very well. And with the recent Alberta Canada pipeline grant bargain, it's reopened EOR as a tool, which is awesome, and then it provides a carrot for the hydrocarbon industry to capture its CO2 emissions and put them into beneficial use, just as it's being done in the United States. We've got three, let's see if I can go to the next slide here. Okay, we've got three great subject matter experts today for today's session. Really glad that they could make it. Richard Baker will be carrying most of the load today, supported by Eric Delamaide and Ali Telmadarreie. And Richard's got a master's degree in petroleum engineering and over 40 years of hands-on experience in reservoir engineering, simulation, carbon capture and storage, enhanced oil recovery, and thermal projects across 53 countries. He's authored the book Practical Reservoir Engineering and Characterization. Distinguished author, member of the Petroleum Society of CIM, and has received multiple SPE awards. He'll unpack what EOR is, for those of you that don't know what it is, where it makes sense, and the Alberta CO2 EOR or disposal value propositions. So he's got a great section on that. Eric is General Manager at IFP Technologies. He has a master's degree in petroleum engineering. He's a reservoir engineer and is an EOR expert, being involved with over 100 EOR projects, including 40 polymer floods. He has published over 90 papers on reservoir engineering and EOR and has served on multiple conference, technical committees, and workshops. He is a former chair of SPE, Distinguished Lectures Committee, and received, again, numerous SPE awards. And Eric will highlight progress in the chemical EOR sector and its value proposition. Ali Telmadarreie is the CEO and co-founder of Cnergreen Corporation. He has a PhD in petroleum engineering with research in foam flow, nanoparticle chemistry, and conformance control, and is committed to advancing EOR performance while enabling practical CO utilization and storage. Ali has overseen multiple Armorfoam field pilots across Canada and U.S., and he'll discuss advances of use of Armorfoam to augment EOR techniques. The other EOR techniques, and Richard will cover it, is a slide on it. We've covered solvent and thermal in prior sessions. We're not focusing on that today, and Richard has a slide for that. So I'd like to please welcome Richard to the podium, and look forward to a good session.
Well, it's Nice to see people that I know in the audience. It's always a little bit better than a bunch of hostile people for me. But I'm really glad you guys come. I hope this is informative. I know this is very topical type question, but let's just start. And I know from most of you, who at least the people I know, that this EOR part is going to be a little bit review, but I'll go through it quickly. And I just want everybody off in the same sort of level here, because I know that there's, I better point it over there. Okay, so what is EOR? Well, basically, it's a collection of techniques, and you're trying to improve recovery from primary recovery, just pumping the oil out, or maybe water drive, and or water flooding. Okay, so you're trying to improve recovery higher, and it consists of two components. Basically, displacement efficiency, which is like, think of it as a unit, microscopic type of improvement, where you're reducing things like interfacial tension and whatever, and allowing the rock to be better scrubbed. And then the second aspect is to improve sweep efficiency and whatever. So if you look at the diagram on the right, I got to get this right now, left-hand side in terms of the lower, that's what a classic water flood looks like, with a schematic view with an injector and producer, and we're injecting fluids into that reservoir, and we don't get perfect displacement efficiency or perfect volumetric sweep efficiency. So what we like to do in EOR is what I show on the right-hand lower side, is I want to inject, let's say, a polymer or surfactant, and the polymer is going to get me better volumetric sweep. So if you look at my little cartoon there, it improves in volumetric sweep. And then if you look at displacement efficiency, the surfactant scrubs the rock, or a CO2 will scrub the rock better. Okay. Come on, there. Okay, so if you look at the diagram on the left-hand corner again, the one I showed you previously was surfactant and polymer. Now, with CO2, because CO2 has a lower viscosity and also has a tendency to override in a zone, you get generally poor sweep efficiency in CO2, so you don't necessarily contact the same amount as, let's say, Eric would do in a polymer flood. Okay, and what are we talking about today? Basically, we're talking about three areas. We're talking about CO2, we're talking about polymer and alkaline and chemicals, and then Ali's going to talk about nanoparticles and surfactants and whatever. Obviously, EOR is huge. I mean, we could, if you let me talk, I could talk for a week on all the EOR in the world. You'd all be asleep then. But we're just going to focus on these three today, and then sort of look at how we're applying that technology. And I think, let me just start here. Okay, so let's talk about, this is a good friend, Eric, and he knows about as much as anybody else in the whole world in terms of chemical flooding. So I'll let you take it.
Thank you, Richard, for the introduction, and thanks everyone for attending. So let's see if I can get this right. So yeah, Richard already started talking about EOR and explaining a little bit how it works and what are the goals. So on the chemical EOR, from a chemical EOR standpoint, we are dealing with three components. The first component is polymer, which can be used by itself. And really, polymer is a powder that you dissolve with water, and it makes water more viscous. So that's the part of the mobility ratio improvement and the sweep efficiency improvement that Richard was describing. The second main component is surfactant, and Richard talked about that as well. So surfactant is there to reduce the interfacial tension, and really, as Richard is putting it, scrub the rocks. Okay, so we really want to reduce the residual oil saturation, which neither water or polymer can displace. Polymer does not reduce the residual oil saturation. Okay. So those are the two main components. And then we have the third member of the team, which is alkali. are different types of alkali, but basically alkali has several uses. It is generally used in combination with surfactant because it can either generate surfactant in situ by combining with the oil, which is present in a reservoir, and the other use of alkali, it really reduces surfactant. And I talked about that surfactant is extremely expensive, so you don't want to waste a lot of surfactant on the rock surface. Okay, so those three often go together. Polymer can be used by itself, and then surfactant and alkali normally they don't go by themselves. It's very seldom that they are used themselves. In most cases, you have polymer at least in order to provide the mobility control that you need. This is a graph of worldwide expansion. So when I'm talking about expansions, I'm not talking about small-scale pilots. I'm really talking about large-scale expansions with dozens or even hundreds of wells injecting the chemicals. So Canada has been really at the forefront of chemical EOR. Well done, Canada. And then, of course, China has done chemical EOR for as long as I can remember. But there have been some interesting developments in the recent years that I want to point out as well. Argentina, in the south over there, has done lots of projects, but mostly polymer, at least the large-scale projects. The US has woken up after a few hundred polymer flood pilots. They have managed to get one large-scale polymer flood in Alaska. They have realized that heavy oil, whether it's in Canada or in the US, it's still heavy oil. So if it works in Canada, it probably works in the US. So, and they are getting really good results. And then another very interesting novelty is in offshore UK, where they are doing polymer flood. Polymer flood, for a number of reasons, has always been used on 99 or even 99.9% of the polymer floods are onshore. But there are a few polymer flood offshore, and this one is really a novelty started by Chevron a few years ago or many years ago. There is a huge one in Africa, and then India has really taken off these past few years with very large-scale polymer floods and even a large-scale surfactant flood as well. There are a few in the Middle East. One is quite interesting. I want to point it out. It's a wettability modifier, so they use surfactant, but for a different reason. They are not targeting the interfacial tension, but the contact angle. So I'm not sure I understand why it's working, but it seems to be working fairly well as well. Okay, it's in Qatar. Okay, so now let's look at all the processes separately. So polymer flood, as I was saying, has been really a huge success. It's really a very robust, proven, and commercial technology. We have lots of polymer floods in Canada, Pelican Lake being the largest one, but you have Cactus Lake, you have Bodo, Cosine, et cetera, et cetera. And then there are many other projects that have not been published, but are still ongoing. If you look at the bottom of the screen, I've tried to put a kind of viscosity scale, oil viscosity scale, where we can apply polymer. So basically, it goes from the light oil, but to be honest, when you have light oil, 1 CP, like they have in Sirikit in Thailand, you're not going to get a great improvement because the mobility ratio is already very low. So how can you improve it further? Okay, and then the other side of the scale is the viscous stuff. So how viscous can you go, really? From my experience, above 10,000 CP in reservoir conditions is going to be really tricky. So anything below that, you're good. But if you want to try above that, it's going to be very difficult. And at the bottom, you have the various large-scale projects that are that correspond to the various viscosities. Okay, what are the challenges with polymer? I told you a lot about the good things. There are still a few issues. The limit in permeability, how low can we go? Because polymer molecules are fairly big, so you cannot inject them in unconventional, for instance. Okay, it's never going to go through the very small pore throats. I would say like 20, 30 millidarcy, you are starting to have problems. So above it, it's okay. Below it, a little bit tricky. There are a few tricks that we can use to deal with lower permeability, but it's not straightforward. And then high salinity, high hardness. We don't have a lot of that in Canada, but international. What I have here are the examples that are at the bottom correspond to a reservoir in Kuwait where they have almost 260 grams of salt, 260 grams per liter of salt. So this is really pushing the polymer to its limit. On the right-hand side for this same water, you have the polymer resistance with time, and we see that it's really difficult to find a polymer that is going to withstand those conditions, especially when temperature is high. In Canada, again, not a problem. Often temperature is lower, but that's one of the limitations. Surfactant, so as I was saying, surfactant is really reducing the interfacial tension, and it can be used to change the wettability. It's also important, as the project in Qatar showed. And really what we are trying to achieve is to reduce the residual oversaturation, okay? Polymer doesn't do that. It's expensive. Like, to give you an idea, a polymer, typically $2 per kilo, surfactant, 5 times that, okay? And then it absorbs a lot as well, much more than polymer. So a lot of times the economics of surfactant injection is a bit tricky. So, and as I will explain in the next slide, you can use alkali. So basically, on the right-hand side, you have an example. This is just a core flood, but the first part of the displacement is injecting polymer. That's the green curve. So you inject polymer for a while, and then you're really stabilized. There is nothing else that you can gain by injecting polymer. If you inject surfactant, you see the jump. That's just the red part of the curve. You see that all of a sudden you are mobilizing a lot of the oil that was trapped that you could not mobilize with either water or polymer. And now you are mobilizing it. And then if you push it with polymer, then you can really get it out of the formation, okay? Again, that's a core flood. But in the core, we can get almost 100% of the oil. After that, we have the heterogeneity of the reservoir and all of that we need to deal with. But still, if you don't get a good result in the core, it's not going to work in the reservoir, okay? So, yeah, a lot of difficulties for surfactant, higher TDS. It increases the absorption, higher hardness as well, so you have to deal with all those things. And then the clay and the limestone, for instance, increase the absorption of the surfactant, which is very costly, so you want to minimize that as much as you can. So in order to minimize it, you can try and use alkali. There are a number of alkali, and as I was saying, the alkali can generate surfactant and reduce surfactant absorption. And you have on the right-hand side a diagram which shows for most of the published cases what kind of concentrations we are talking about. So on the x-axis, you have the alkali concentration. It's in percent, so it's 10 grams per liter to up to 30 grams per liter. And then you have the surfactant concentration, which is typically less than 1%. Okay. It requires soft water. Alkali doesn't like hardness. And at the bottom here, you have this very scary slide that is coming from the Tabor ASP flood in Canada, where they had great recovery. I mean, they increased recovery factor by over 10%. But they had huge scaling issues because of the alkali mixing with the hard water, and it was not a very, very hard water. And they could never find a solution like scale inhibitors and things like that were not 100% efficient, okay? So this is really the limitation of alkali. If you don't have soft water, it's really difficult. And then, yes, last but not least, this is my last slide, but what is really important, especially in the context of this discussion, I suppose, is that chemical EOR can really help reducing the carbon emissions, okay? So it's not 100% efficient, but it helps a lot. This was, I mean, one of the first publications on that was by Fares Zadeh. And what he explained in his paper, which is quite interesting, is really where you spend a lot of, where you generate a lot of carbon emissions when you are doing a water flood, for instance, is when the water cut increases. And the more water you have to produce, like we've seen, you know, water floods operating at 95, 99% water cut. So it means that for every barrel of oil that you produce, you have 99 barrels of water you need to deal with. So you need the pumps, you need to, big facilities, and this is what really causes the emission of the carbon emissions, or a large part of it. So the idea is if you reduce the water cut, and polymer flood is a great help for that, you can really reduce the carbon emissions. There should be something, oops, nope, that was a big mistake. Sorry, I have to go backwards. If I can, I pressed too much. Yeah, one more. I thought there was an animation on that one. Oh yeah, here. Okay, I was too quick. So yeah, I mean, we can do a carbon analysis if you want, where we see, okay, how much do we gain by reducing the water production, and how much more do we spend? Like, we need to manufacture the polymer, we need to transport it on site. So there are pros and cons, but when you do the balance, and this is just a study that we did recently in the Middle East, for instance, if it wants to show up. Yeah, here. It shows as time goes by, so you have the orange, which is the orange curve, which is the water flood, and the green curve shows the performances of the polymer floods in terms of CO2 emissions, okay? So really the polymer injection helps you reduce the the carbon emissions significantly, depending on the cases, but 20, 30, 40%, that's not unheard of, okay? So I want to stop here, basically, sure, Richard, thank you.
Okay, I'm just going to give you an overview of where CO2 flooding is worldwide right now, and particularly really talking about North America here. So I plotted here just oil rate in thousands of barrels versus time. Now, what you need to understand is we've been doing CO2 floods since 1973 in Texas. So it's a relatively mature technology. Now, there's always different combinations of heterogeneity and fractures and stuff like that that make things novel, and also, you know, horizontal wells and all that kind of stuff. But it's a relatively mature type of project. And where I got this data is basically Steve Meltzer, a good friend of mine from Midland, Texas. So he has a CO2 conference every year in Midland around December, and then I've taken that from him, and I took it from him today when I talked to him. And then the rest of the data, it comes from Advanced Resources International. They're out of Washington. So what I'm plotting here is oil rate in the United States, and I'll talk about Canada in just a sec here. And you can see how much growth there has been historically in it. And so you can see, like I said, we started off in 1973, 1974 in terms of with pilots, but they were commercial level pilots in West Texas, and it's grown since there. Peaks about 320,000 barrels a day. And the last few years, it's definitely had more of a downturn. There's been less incentive, primarily because of the shale gale, and then just terms of pricing uncertainty. The same things that affect oil sands and stuff like that with us. Same type of arrangement. Okay, now this is from Advanced Resources International again, and I wanted to show you this because I think it gives you a good idea. It goes from 1986 to 2022, and you can see it's broken. Again, this is U.S. oil rate, and the data is from about 2023, and you can see a steady growth. Now, what you can get from this slide is there's been 3 billion barrels of incremental oil. That's an impressive number, okay? It shows you how well the CO2 system, and I'm going to keep that in the back of your mind here, system works in the United States. Okay, and they have stored over 375 industrial CO2 storage. So it's not stuff that's gone out of the Denver area into from a CO2 field. This is industrial CO2. So they've done about 375 megatons, okay? And they do it but all my values will be in megatons per year, okay? Now, if you see how that compares already in Weyburn, Whitecap would tell you it's around 40 megatons of CO2 that they've stored already, okay? So this is industrial source CO2, and keep that in mind. Now, when you place, hopefully this will work. Come on, baby. Oh, there you go. It just has a little bit of a delay. Okay, so when you compare about aquifer injection, so there's thing I need to understand, you need to understand there's CCUS, and I'm using U as in utilization, not underground. Okay, so I'm talking about this is benefit, a benefit to somebody, and it has a business plan associated with it. They have stored that CO2, and you look at what the worldwide amount of CO2 we've stored in aquifer, it's about 50 to 65. It's a range, you can't exactly determine it because it's not everybody reports CO2 in the same way, but it's say 50 or 60. So it's about 6 times more what they've stored in West Texas, well, Texas and the United States right now compared to what all of the aquifers in the world have done to date. So it's a little bit, I agree that aquifer storage will grow with time, and it'll probably surpass EOR, no doubt about it. But right now, it's like a 6-to-1 ratio. So we're talking a little bit of apples and oranges here. And you can see here, where just Weyburn alone, my old project a long time ago, it had stored about 40 megatons per year. Oh, don't do that. Okay, and this is from Steve Meltzer again, good friend of mine. So from 1992, all I want you to do is look at the number of that they looked at worldwide. There's not a lot of updates on this, which is kind of unfortunate. I guess we're all succumbing to the chat GPT world. But, so from 1992 into about 2018, you're at about 165 projects worldwide. So this, I don't want to give you the idea that CO2 flooding is brand new, okay? How you apply it in your fields, yes, that there is changes in, and you know what Ali will talk about, nanotechnologies or polymers, whatever, that stuff is evolving, but I think how we handle CO2 floods really isn't a brand new novel thing, and I don't want to pretend that it is. Okay, so with that, I'll let Ali talk up a little bit more, and we'll go from there.
Okay, thank you, Richard, and good afternoon, everyone. So it was a very good introduction about the, Richard mentioned at the beginning about the sweep efficiency and mobility control. And we know that CO2 viscosity is much lower than the water. And Eric mentioned that they add polymer to the water to improve the viscosity of the water. And what we are doing at Cnergreen, we are trying to viscosify the CO2 basically to improve that mobility ratio and improve the sweep efficiency. So today is only 9 to 10 minute presentation. And what I'm going to do, I'm going to share our nanoparticle-based foam technology, Armorfoam, that we have deployed in several pilots in Canada and US, and a little bit share some of those results today as well. So you have seen in one of Richard's slide that CO2 oil rate in US is toward the declining area, but that could be due to several reasons, drilling or not enough expansion or budget. But one reason could be the sweep efficiency and CO2 utilization on those projects that toward the end of the life is mature, now CO2 is recycling. So that's the exact problem we are trying to solve at Cnergreen. So these schematics here shows the problem statement. On the left, a status quo is a typical injection production well. Water fluid you are injecting underground here, CO2, water, even polymer, chemical surfactant. We'll try to find a path of least resistance between injection well and production well. So at some point, you end up with a short circuit like this. So whatever you inject after that will try to find the same path and recycle back to the production well. So that will reduce the efficiency of the flood, basically. What we do at Cnergreen, we inject that Armorfoam, nanoparticle-based foam underground. We'll go to the same path of least resistance because it's an easier path for the fluid to flow. But because it's viscous and stable, remain on that path. So when operator resume their injection in the third schematic, we'll divert the injected CO2, water, or any other fluid toward untouched part of the reservoir, access more porous space for oil recovery. And if you're using captured CO2, we can also store more CO2 underground. So in terms of enhanced oil recovery, this is applicable to most of any fluid you are injecting underground, as I mentioned. But you can also think beyond EOR as well. So if you're injecting, CCS is one example for aquifer storage, but if you're injecting water to extract heat from the rock for geothermal, you want to maximize your contact to the rock to extract that heat more efficiently. This is applicable to that. If you're injecting water to push a lithium-rich brine to the production well to extract that lithium more, so this is applicable to that as well. For the sake of this presentation, we are currently focusing on CO2 EOR mainly and EOR in general, but just give you a sense of other application that this technology has. So this slide, I'm not sure if you can play the video from the panel over there, but this slide shows the quick video how Armorfoam works compared to the conventional surfactant foam, as Eric mentioned that. So one of the challenges of surfactant foam, beside absorption and contact with rock, is when in contact with crude oil, it collapses very fast, relatively fast. So this left jar is filled with oil, a surfactant foam is added to that jar, and the right is Armorfoam, basically, made with the same surfactant. And that surfactant is very good foaming surfactant, has been used in a pilot in Texas, very successfully, technical success as well. But what I'm trying to show here, how we can make it even better by adding nanoparticles to improve the stability of the surfactant-based foam at reservoir condition. What it does, it will help us to reduce the chemical costs. Now we can inject less chemical because the foam remains stable for a longer time. We have seen in our pilot up to 6 months or more just by injecting few days or weeks of chemical injection. And also help us to tailor make the product to a specific reservoir condition. So I want to mention Armorfoam is not a product, so it's a process of making a stable and strong foam for underground application. And the reason behind that is on those SEM or microscopic image that you can see on top right and top left, showing one individual bubble of foam basically under microscope. On the right is Armorfoam bubble, on the left is surfactant-based foam. So we are covering each individual bubble with a layer of solid nanoparticle. That will help us to reduce adsorption to rock, reduce contact or interaction with the oil, and also high salinity. So keep the bubble, hence the name Armorfoam. We are armoring bubble, so keep the bubble more stable at reservoir condition so we can inject less chemical and improve the project technically and economically. So in the next slide, I'm going to summarize some of our pilots that we have done so far. So this table shows some of our pilots. It's not all of them. As we speak, we are doing 2 more pilots, which are in the progress. Mainly, these are on CO2 injection or CO2 alternating water injection. There is one pilot that is produced gas injection as well, and they have all conformance issues, sweep efficiency issue, high CO2 production rate, meaning that the recycling rate is high. But if you look at the right side of the tables, incremental oil rate, these are the benefit that we have seen after Armorfoam treatment. That's very clear, incremental and oil rate. But what I want to talk about is on the CO2 saving column. What I mean by CO2 saving here is this is the amount that operator inject less to get that incremental oil. For example, in the first case, 20,000 less tons of CO2 have been injected to produce that amount of incremental oil. So that significantly improved the project economics and also the efficiency of the flood. So in some cases, we have seen up to 50% CO2 utilization improvement, which if you translate that to the field scale will be significant. So that extra amount of CO2 that operator saved on that well will be diverted to another well and produce more oil. So if you look at the field scale, that will increase the project economics significantly. The other consideration that we haven't done here is the CO2 storage. I mean, if you look at the literature, there's a lot of data that shows that for every incremental barrel of oil that you can produce, anywhere between 0.2 to 0.8 tons of CO2 you can store. So you can easily calculate or estimate how much extra CO2 you're going to produce by using such technologies. I think Richard is going to talk about the potential incentive on CO2 EOR, and that will be game-changing for these kind of technologies, because not only we can also improve the oil, but increase the CO2 storage as well and bring another revenue stream to operators. In the second to the last slide, I'm going to quickly share one example of one of these pilots that we have done in CO2 EOR, which is also alternated with water injection. So these plots, on the y-axis, you see the oil rates. I intentionally removed the units. On the x-axis, you see the injection days. On day 0 is the day that we start injecting Armorfoam. It has been only injected for 5 days, so it's a very short treatment program. In this case, depending on the application, we have seen some cases for months or 2 of injection, but the shortest we have was 4 or 5 days of injection. This well particularly is very declining in terms of oil rates because of high communication and that problem that I mentioned in the schematic. CO2 is showing up in the production well very fast in a matter of 12 hours. So when the operator starts injecting CO2, 12 hours later it shows up in the production well. So that's why the decline rate is very fast. And they are also injecting water with CO2. It's not a pure CO2 injection. It's mainly on water and some CO2 cycle in between. So you can clearly see after the first injection of Armorfoam, a few weeks after that, we have seen a significant jump in the oil rate, triple in some cases, even quadrupling the oil rate compared to the baseline. It lasted a few months and then slowly goes back to the baseline. That's where we do the second treatment. And if you look at the second treatment, we also see the same response. Oil is increasing, this time more sustainably and for longer time. And this is the latest data I have, is still oil is above the baseline, with only 5 days of injection. So if you look at the conventional surfactant-based foam technology, you need to inject for several months or even up to a year to see something, because you need more chemical to establish a good foam to see these kind of benefit. Of course, this is one case by case is different. We had the case that we had to inject this product 20 days a month every quarter for a full year to see, because it was much larger reservoir, much larger communication. The volume depends on the reservoir behavior, basically, and reservoir performance, basically. So in the last slide, I want to quickly touch base on other application and benefit of the technology, basically. So the map on the far right showing the location of pilots so far, mainly in Canada. We have a couple of ongoing in the US. There's a couple of more that I haven't included in this map. We just started recently, but all of them in North America. Beside the CO2 EOR CCUS, another application we are working is water flood application. So it's not necessarily like polymer that you're completely changing the viscosity and continuously inject that. Is augmenting the water flood or even polymer flood to improve the sweep efficiency of the water injection, just with short treatment of the foam, and then you go back to your water injection. The reason we think it works is because this technology can be tuned based on the viscosity. So we can tune the viscosity of the foam to be in order of few centipoise to 100 or even thousands of centipoise to improve the sweep efficiency. In Q1 or Q2, we are going to deploy one pilot in water flood, but the previous slide I showed you in the field, that was mainly on water cycle, and most of the oil increase we have seen was on the water cycle of the CO2 water alternative injection. So that was a trigger, plus all the lab data we have shows that there's a potential in water flood improvement using this technology, and also any gas injection. Beside the conventional reservoir, we have unconventional reservoir system, like a hydraulic fracture reservoir that people use gas for huff and puff application. So inject the gas underground, contact the oil, soak it, and produce it back. That's another application we are working currently on that. But back to CO2 EOR and CCUS, what we are trying to do is try to improve the sweep efficiency, as Richard mentioned at the beginning, not displacement efficiency, but sweep efficiency, so we can contact more of the CO2 to more rock and access those oil better, and store more CO2 at the same time and improve the project economic as a whole. So if you have any question, you can reach out to me through LinkedIn. I will be happy to answer your question at the end of this event. Thank you.
Just got to write some notes here to myself. Okay. Okay, let's talk about Canada now, okay, and where we are and where we could go, okay? And I want to give you my viewpoint, but I have spent quite a bit of time with this one, like 35 years. So I think my numbers are as good as any's, and I want to just show you where I think we should go. And I haven't shown this to anybody else in the world. Okay. Oh, don't go too far. Come on, baby. Go backwards. Okay, sorry. Okay. Now, Michael and I, who I owe a big favor to, drafted this over the weekend and spent probably 4 to 5 hours on it. And we got to the point of exhaustion. But I wouldn't be selling... Don't sell the family farm on this map, okay? It's just approximate. We had to adjust things and everything. What we did is we took old study that I had done 2007, and you say, oh my goodness, the OIPs have changed in those. But generally, old water flood reservoirs with high recovery factor, the right light oil, and are suitable for miscible flood associated. Those are the green dots, and they're roughly proportional to size, and I've left out pemmicardium. Okay, from that. So you can sort of see, here's the green dots in the situation in Canada here. And then I've also taken what sources were in CO2 in 2007. So they're old, but they still show you generally where gas plants are, fertilizer plants, and that kind of stuff. And then we've also implanted where pathways would go in terms of for taking an oil sands projects, because it's obviously that from 2007 till now has been a tremendous growth in oil sands and that. So we wanted to give you that perspective. But if I had to say something about Alberta and using EOR, the big thing is, I don't know if it doesn't point, but the big thing is lots of CO2 here, okay, lots of industrial in the East Canada, but Eastern Edmonton, not Eastern Canada. But, and then you can basically see where a lot of light oil fields are all in. Oh, sorry, yeah, I've got it. Okay, because I don't think the pointer works here. So yeah, okay. So basically, what you need to understand is ideal world would like to move it from east to west, and that improves the economics quite a bit on that. Okay. Okay, and this is the data from. It'll stay in your slide kit so you can look at the data a little bit better than what Michael and I did over the weekend. But we basically reached the point of exhaustion on trying to make slides perfect and everything like that. But anyways, to go on from that. Okay, now this, I could spend another 5 days on carbon capture and storage, and I'm not doing it justice right now. I'll tell you that right now, is that I would like to spend more time, but I'd be boring you guys all to tears. What you need to understand with carbon capture and storage is it's a growing concern. It's strong, it's there, and whether you like it or not, it's definitely going to be a factor in terms of total storage of CO2. I believe in that totally. And this is a McDaniel map here, and I've hopefully references Francis's map. You can get it from LinkedIn. And basically, you can see the various hubs associated with it. And you can see here a lot of things are under construction or proposed, okay? And that's typical, even with EOR. I would swear that for every 4 projects you have, 3 are always under consideration, and people come up with new ones every year. The actual in-the-ground ones are quite a lot more muted than that. And so just remember, that's a perspective. But it talks about, the thing that's nice about what Francis always presents is that is that he's looking at it from a systems point of view, and I think it's very important to look at CO2 from a systems point of view. Okay, so let's get to where we are here. Hopefully this will... Okay, now I have to give you a little bit of background here. I have to give you a little bit of actually, you know what? I'm going to back up a little bit because I realized I missed something on that last slide. Oh, one more. One more. Okay, on this slide, we also attached how much total storage has been. And these numbers are probably 2003, 2004, somewhere in that range. But, you know, I look at, so if you look at southeast Saskatchewan and you look at Weyburn, you can see there's about 40 megatons of storage. Okay, a megaton per year is equal to 53 million a day. Okay, so that's just to give yourself conversion here if you're in cubic feet or whatever. So 53 is equal to 1 megaton per annum. Okay, now Weyburn has stored historically about 40 megatons of storage. It injects, or it stores about 2 megatons per year, according to Whitecap, and it makes about 18,000 barrels a day of incremental. When you look at Midale, it's stored about 5 megatons. So these are substantial, even from a worldwide perspective. They would definitely be above any aquifer storage that has been done historically. Okay, and then Midale has 5 megatons, and it's generating about 0.1 megaton per year. And it's a little harder to figure out what Midale's is. It's a range from 2 to 5,000. Now, if you look at, let's go to one of my old favorites. If you look at the Clive field, we've stored about 5.5 megatons in that one, and it is injecting at about 1.5 megatons per year, and it has a pretty tiny oil rate, 780. And then if you look at Joffrey, it's 1.5 megatons of storage. And it's tiny rates, and same thing with Chigwell is the same sort of thing. So it gives you a feel, not of where every little dinky pilot is, but where the big volumes have gone. And you can see if you just add up the Canadian totals alone, it's substantial. So we need to take a little bit of pride on that, and I can definitely say for Midale, Weyburn, and Clive, I've had a hand in that. And I'm proud of what we've done here, store and things. So it's practical. It's practical from an economic point of view, and it's practical from a storage point of view, in my opinion. Now we can go forward here. Sorry, you guys, on that one. Okay, now what you need to understand in terms of comes with economics is when you look at it from an emitter point of view, if you look at from a pathways point of view, what you want is a very flat plateau in terms of CO2 injection, right? So a lot of stuff that I'm doing in the States, they want flat plateau. We're taking the CO2 right now, and we're injecting it into aquifers and stuff. So you want that flat plateau, and you want it for a long period of time. Now, when you do EOR production, you get a lot more jagged edge. Oh, okay, jagged edge. So what happens, I better be careful on this. What happens is you start an EOR, okay, and it comes on, and it'll give you the peak oil rate, and then it declines. And then if you want another one, you do a peak oil rate, and then it declines, okay? So it's not giving you that flat plateau, which the carbon emitters would love to have. That's what they want. I mean, that's what they want is, from me, they're gonna say, well, how much security do you have on that from both a capture point of view and a storage point of view? So that's really important. So what we did in this case that I'm gonna show you is we only injected in one reservoir, and then we said, okay, we'll now go to an aquifer case. We'll inject the rest in the aquifer case. But you can improve your economics, obviously. If you look at West Texas and you look at even Weyburn and Midale, the more infrastructure you have in the area, the more capability you have to grow because of the incremental economics, okay? Well, don't do that. Okay, so let's talk about the economics. Now, what are we doing here? I'm comparing saline aquifer values to EOR, and I'm saying, how does this roll out? And I'm sorry, but you know, even the politicians don't know the answers to this. They're guessing, really. I'm going to show you what I think is a believable case, and you can put me on a lie detector and ask me hard questions, and I think I'd pass fairly easily on it, okay? So I'm comparing a saline aquifer to a CO2 project, okay? Now, what I'm going to do is I'm going to do a hypothetical cash flow analysis from it. Now, anybody who knows me knows that I'm not Mr. Economics. I didn't get distinguished authors in economics or anything, so you can take my results with a grain of salt, but still, they're reasonable. They make smell checks that we've done for the last 35 years. They're reasonable. They're not airy-fairy type stuff. And so we're going to assume an integrated company right now for the sake of argument here. And that company has enough taxable earnings to claim full tax credits for it. And the purpose of the analysis is just to look at the two systems. And we're looking at we're using a hypothetical of about 273 million stock tank barrels of oil per day. Okay. Now, when you look at the two cases, I'm going to start with the end, and then I'll show you the methodology we used, and then we'll recap at the very end at it. But when you look at it here, hopefully these things fly in. Yeah, okay. The big thing is when you look at the EOR case, so what we've done is we inject CO2 for about 13 years. We store the same amount, 1 megaton per year at 53 million a day of skiffs, okay? And so you can see that we, at a net present value of 1.3 billion, we have a payout of about 7 years, and we have a rate of return of about 30% with that, okay? And that's using $80 a barrel. It's using a Canadian tax of $130 per ton. That's like the grand bargain here. And then I compare that with the saline aquifer. Okay, now the saline aquifers economics are a lot more timid. Okay, they're not as robust. I'm only making 233 million. I'm at 13% rate of return, and it's a payout of 15 years. So it would never fly in an oil company right now. You wouldn't necessarily have anything that has 15 years of payout, okay? But the real advantage, which I'll get to the very end, is that the system is a lot more stable, and there's tons of benefit from that infrastructure. Okay, so what technical data did I use? Okay, anybody who's smart, if you're Bruce here or anybody who knows that thing, it all depends on your technical estimation of reserves, and it also relies on your economics and your input here. What I'm using is a dimensionless analysis. I have the references in the back because I know some of you guys are going to try the same thing. So I have the references where I got the data. But basically what you need to understand is this is oil right here, and this is the amount of CO2 I inject in the bottom. So it's tying injection with production, and it's talking about incremental. And this technique's been used for over 40 or 50 years. I mean, I think I used it as a summer student in Husky, but not for CO2 floods. But anyways, what you need to understand is this is performance data. I'm going to show you it in a second here. And what we do is put a best fit through that data. So we're designing by averages, which is also fairly annoying too. And then they call it dimensionless analysis, but there's the references in the back. You can handle that too, hopefully. Okay. So why am I doing it? Don't I just take a nice simulation study, and I can inflate the peak, and it looks great for the economics and everything like that. Why don't I just use simulation? Everybody else uses simulation. Surely simulation must be right. Well, from a person who spent 40 years in simulation, if you pick too homogeneous of a model, or if you neglect bypassing or some of the stuff that Eric and Ali talk about, yeah, it looks fantastic on the design board. And that's what a lot of, I would say, aquifer projects today, they look great on a design board until you start, doing it, implementing. I hate to use the term, but boots on the ground type of stuff. Okay. Now, I keep doing that. Okay. Okay. Now, I got to do one more. This is annoying. Oh, we'll forget it. We'll do this. So what I want to show you is what we do is we take 30 projects from Texas, Weyburn, we look at Joffrey, and we combine them all into a design curve. And if you look at the far graph on the right-hand corner, upper there, you can kind of see the design, what we used in there. And there's a whole bunch of more floods associated with that. But that's kind of our design. So if you look at that middle red portion of that curve, that's our design. So if anything, we're quite conservative. Because remember that you're looking at here, you're looking at oil rate, and then you're also looking at CO2 injection in the bottom. So we didn't cheat, like we didn't go and say, oh, I'm going to take the upper curve, or I'm going to take a simulation model and a homogeneous reservoir. We picked, this is field data. I really want to stress that. Okay, now what we also did, again, for my friend Steve Meltzer and that in Texas, was we took the Texas CO2 floods, and we took the also Weyburn, and we know how much retention. So roughly, just roughly, for every 2 molecules you inject of CO2, you produced about 1 of them back, but they vary with time. So if you look at CO2 retention, it's like on the blue dashed line here, and then CO2 production is in the red dotted line associated with there. So we're using field data here. I really want to stress that. Oh, okay, the animations don't work quite as well. Okay, so let's just keep going. So you're basically, think of 2 to 1 in terms of injection. Okay, let's look at the economics, because I said it's a function, the economics is a function of what production forecast I have and what values I use for economics. And if anything here, I'm a little bit too liberal with, or I put too much capital cost in the EOR case, and I could have tuned it to make it better, and so I could get you down to 5 to 6 years payout, but this is a pretty good estimate here of what we've done, okay? Okay, now, one thing I want to do is frame this problem for you, okay? It's when you're doing economics of CO2, and whether that's CCS, aquifer injection, or CCUS, CO2 EOR, basically what I'm doing here, is it's a function of a lot of variables, okay? Yes, surprise, surprise, oil price is a big barrier, is a big concern, but also what your CO2 tax is. And the nice thing about what Carney and Smith did is it gives me a target, where before it was kind of floating in the space. So I use about $130 CO2 tax here. The other thing that is a function of what is your field cost. So we're dealing with old fields, we're dealing with legacy wellbores, and we're dealing with old junk. And the way I describe it is here, what we're doing is it's like fixing up a house. Like when you buy your first house, it's not going to be pretty as a $6 million house in the middle of somewhere you dream about, but it's going to be practical case. So we put in the field case, and that constrains it, and then also pipeline constraints are a concern with this. So as I told you right at the start, what you really want to move is CO2 from the oil sands area into central Alberta or central Alberta or western Alberta, okay? And these are the kind of costs that are associated with. They're all, you can, if you read the references, you can see where I'll get all my costs, or just ask me later. And what you're coming up with is an oil production profile associated with that, and that's going to vary and everything like that. But basically what I did is I put 100 kilometers of pipeline. Remember, what I'm going to do here is I'm going to take the quest as spent, okay, from 2020 progress report. You know how much Shell spent on their plant. And I'm going to build that plant again. And then what I'm going to do is, for the case of EOR, I'm not going to use the injectors initially, but I'll bring them back in. And then in the case of aquifer injection, I just use Shell's CapEx and OpEx as spent. And we use the exact same thing. So I didn't want to distort my picture by giving you overly optimistic results or anything like that. And then we used a 5% royalty rate for Alberta, which is standard practice for EOR. Okay, so what's the difference between the two? Okay, so the top is the saline aquifer, the CCS case, and it's pretty straightforward because Shell's already published all this stuff. It's annual report. it's referenced. So you take that, you do a cash flow model. The only thing we're doing is we're running it on $130 a ton in terms of a tax, and then we're getting payouts, net present value at 10%, IRR, and cash flows. Now, in the EOR case, what you're taking is those same costs and operating costs for the plant. You're subtracting out the well cost. So I'm not drilling into an aquifer initially, but I do drill into it about 13 years later. And then I add a pipeline cost and add OPEX and whatever. And those are basically the stuff that I've really added to this whole picture in terms of cash flow model. So what does it look like? Okay, so if this is my base case, I run it at $80 a barrel and $130 a ton. I get about a 30% rate of return at a net present value of $1.3 billion. It reaches payout of about 7 years. So you're going to see 7 years versus 15 years with a pure CCS project. And then what I do is when we run this thing, I think for 13 years or so, and then what happens is, so we run it out for 13 years, that's what I just pointed out to. We're going to run it out for 13 years, and then I drill those injectors. So I drill the same injectors that were in Quest and add that to capital. That's why you see the net cash flow goes down here. And you can see here where it reaches a 7-year payout. Now, when you look at the price sensitivity of it, okay, so like I said, there's field costs, there's taxation strategies, and then there's also price of oil in here. You can see how it varies with the price of oil, and surprise, surprise, I mean, it depends on the price of oil, which isn't shocking here. So if you look at, we ran it at 50, 60, 80, and $100 a barrel, okay, US dollars, and then we ran the CCS case, so the straight aquifer injection. So we pretended like they all started in 2028, and we ran the saline aquifer case, and then we run the other. And you can see the big advantage here when it comes to, you've got a 7-year payout with $80 a barrel, and then versus a 15-year payout with just a straight CCS project. It improves the economics. Is it the best thing since sliced bread? No. If you went to Bruce Carey's talk, he's talking about clear water, all that kind of heavy oil stuff. You drill a well there, you're getting 6-month payout, right? It can't compete with that. I don't want to lie. It's still a capital-intensive type project, but it improves the economics. So it's if you can build, especially if you can build on an existing infrastructure, it helps a ton. And I mean more surface infrastructure, not so much subsurface. Okay. So you can see here, I put this capital program together. You compare the two. So I'm at a net present value at 10%. I'm about 1.3 versus, now that one is slightly different. That's a 160 million. I must not have updated it properly. But it's a 7 versus a 5. And your rate of return is, it should be 29 or 29.6 versus, what was I at? 13th. 13% internal rate. Sorry, you guys, I missed that. Okay, and so what you can see here, it improves the economics. It's not like going to make you fabulously wealthy all at once. It's still a lot of work for an EOR project, and I don't want to. But what I really want to stress is what I show on the next slide. Okay, now the situation we have with aquifers in Canada is, you have carbon tax, and that depends kind of on what politics or what governments in which, Alberta or Canada, right? So it's a very fragile system. It relies on taxation revenue, and even then, your economics are very, very, very skinny, okay? So it's a long time per payout. Why does EOR be so important in it, okay? And remember I showed you where they had, 345 or 355 megatons of industrial storage in the United States. Why are they able to do that? Well, it's because they're relying on system as opposed to one point type of thing. So what happens when you add EOR into it is it becomes way more stable in terms of it. Why? Because now I can use the CO2 either in an EOR situation or in an aquifer situation. In fact, a long time ago, SAS Power asked me, okay, we're thinking about an aquifer here. We're thinking about aquifer injection, and how does that fit with, you know, I was on the EOR side of things, the CO2. How does that fit with the aquifers? And my reaction is, from an industrial point of view, or an economics point of view, it's much, much more stable. Okay, because you have lots of levers how to control it, and it doesn't become one project has all, okay? Oh, go like this. Okay, now I give my explanations in the next 2 slides in writing, and I know most people, I hope most people will take the presentation. I lived in London, okay, and you know, I could have had a car, the company would have paid for my car and all that. I never had it. Why? Because I prefer to use the tube, okay? And why? Well, when you look at systems, we really need to consider systems here, not just straight one project type things. The tube in London, I think, was around 1870, 1860, in that range. And when you look at it, nobody in their right mind, if you said, okay, I want to build a London tube right now, and I want to have any kind of scale on it, the short-range economics would always say, don't do it, okay? In fact, it's going to take you too long to do it, okay? But if you look back now at London's subway system, it is an amazingly profitable, it's an amazingly used system. And that's true with railroads. So you think of railroads in Canada and how we brought BC into the Confederation. You look at the St. Lawrence Seaway. You look at power grid systems. Anytime we make a system, it usually improves the economics, because not only does it have more inputs and outputs, but it also, most importantly, it means that other fields can come on. So when you look at that Texas oil rate, and you say that, gee, it peaked at 320,000 barrels a day. And yes, it's dropped, okay? It's not as favorable as it was. But at the same time, right now, I know there was pipelines in the companies in the States that went for good premiums right now. Why? Because it's infrastructure and systems thinking that's so important to solving our problem. And so I think this is the most important thing that I have to say. You know, if there's one thing that I would say to a technical audience is, let's stop thinking of one little project. And I know you guys have to justify each project to your board of directors, and I know it's a pain. So I don't want to make light of that. But think of it in a systems way. The benefit hugely outweighs thing. And if you add EOR projects onto it, it will make it better with time, okay? Now, I've put a big long, because I'm so passionate about it, I put my own descriptions, and I got this, I wrote it initially, and then I did it through chat, okay? And I made it better so you could read my writing and get the feel, but it's extremely important to think of systems. And so I always laugh when I listen to politicians how it's all simplified. Oh, I just use 6 MCF per barrel, away we go, and the economics are great. The economics are bad depending on which side you are, but they don't think of it in a systems type way. If you look at oil sands, railroads, St. Lawrence Seaway, etc., a lot of the benefits we have is because of the infrastructure. So I'll get off my pedestal and finish the rest of this talk. Okay. Okay, so you can stop listening to me. Now, so if I was summarizing things now, what Eric says is undoubtedly true about chemical flooding. It's had a huge success. It's had growth. I've been involved with projects in India with it, and what he's telling you is true, okay? That it is, I think it's an undervalued thing, to be honest with you. And there's lots of good examples. It's a maturing technology, and it's more maturing because of the surfactant and nanoparticle type thing than just the straight chemical. Surfactant and polymer, it's still ASP. You can start to see in India where they're starting to challenge some of that stuff, and it's on big scale. Like, it's not like, we're not talking about some little rinky-dink core flood here. We're talking about tens of thousands or hundreds of thousands of barrels incremental from that. Okay, and chemical, what he stressed was that chemical EOR, because you're cycling so much, and you do cycle through heterogeneity, through induced fracture, there's all those things that really They're time consuming to correct them, but what Ali says and Eric says is basically true. When I talk about CO2 EOR, it's pretty established, okay? I don't see, like I've been involved with Clive, I've been involved with Weyburn, Mydale, whatever. It's not rocket science here, you guys. It's yes, you're gonna have to put some judgment factors in there. You know, I noticed there's a lot of people from Tundra. You're gonna have some adjustments when you're doing that, and they've done a great job in some of their stuff. And don't forget about, because there is short circuits in real reservoirs, and even though I'm designing on the average, definitely I think what Ali says about foams and nanoparticles are true. So finally, when you look at the economics, EOR definitely has a big impact on terms of the economics. It roughly cuts your payout down from 15 years down to 7 years. And it almost makes, and I could have made it 35%, maybe not 40, but rate of return, whatever, if I cut capital. But I tried to keep it fairly honest, and it's consistent what you see economics in Louisiana, economics in West Texas, and stuff that I've taught before here. It is price dependent on. It does depend on the regulatory environment, and it's good economics, but it's not outstanding. And I also included my reference list like I promised. And I think that's it, isn't it? Hopefully. Oh, no. Yeah, the other ones this is more infrastructure type stuff. So, Roger?
Okay, we're going to open it up to questions.
Graham Hack with Carbon Alpha. Richard, this is probably a simple one, and I think there's enough capital in your EOR model to cover this, but did you assume that I could basically get access to a depleted oil pool for a song? Or basically, put another way, that my reserve cost is zero?
Fair enough. Yeah, I'm not adding purchase price of an oil field. And to be honest, I think the best people are positioned, I know this is depressing to the oil company guys, infrastructure guys are better positioned for all this carbon capture, because the ones that I'm involved in the States with right now, they're all infrastructure, midstreamers, that kind of stuff. And so, yeah, there is a purchase cost, but it's pretty, that cost would be relatively, I think I put 440 million barrels or dollars into it, so I put a lot of field cost into that. I've put you all to sleep now.
I apologise, this is a basic question. It's Henry Williams, Thor Resources. But when you're injecting the CO2, it's going to be in liquid super state. How long does it stay in that liquid state during the process of EOR and then production at the far end?
That's a good question, and I'll repeat it. The gentleman basically said, when you're injecting CO2, it's in a liquid state. And if you're injecting it, let's say, into a depleted gas reservoir or even a miscible flood, what state is it in? And that's some of the issues you come in, especially with depleted gas reservoirs. Okay, most EOR reservoirs, CO2 in Canada and the United States, are all in what I call the single phase type region. So you're liquid on the surface, you're subcritical in there, so it stays there. However, the big issue is if you're, let's say, using CO2 to repressurize the reservoirs, there's dilemmas with that in terms of the wellbore, and especially when you're looking at a field like Sleipner in the North Sea, where you've got really cold wellheads and low pressures, that sometimes can be, you're reaching phase transitions in those wellbores. It's not a trivial point. I didn't mean to, I hope I didn't oversimplify the CC. Like I said, I could spend a week talking to you about CCS as well. Straight. Good question.
Hi, Jeff Allison from Delta Cleantech. Can you tell me what you expect the grand bargain will, how much it will increase enhanced oil recovery in Canada?
Whoa, that's a tough one. Okay, I'm going to stick my neck out way out. But I think it can do 3 to 4 times more than what we're doing right now, right? Especially if we can get a lateral. Okay, now I helped start Enhance. So I have shares in Enhance, you guys. I'm sorry about that, but I do have shares in Enhance. So I might be biased with my answer here, but I'm not biased. But the big thing is we need to move some of that CO2 to the west, okay? Once we tie on to something like Clive and like Wolf Stream, and that will tremendously open our options. So you kind of know where I think the best, because of Enhance, you kind of know where I think some of the best reservoirs in Alberta is. So I think we can easily, triple that or quadruple that. Now, I might be dead by the time that's all done, but I think it's definitely doable. When you look at the growth curves in Texas, and you look at growth curves in oil sands or Montney, or wherever you want to look, if technology enables, and I think we're in an infrastructure lock situation, and you have people who are passionate aquifer CCS people, and you have passionate EOR people, and I think we need to listen to a little bit to each other and come up with a solution. And so I think if I use EOR, CO2 in West Texas, you can get an idea of how much that infrastructure is important.
We just have a question online here from Kate. Are there likely to be differences in containment and monitoring costs between EOR and saline aquifer storage? And did you account for this in your economics?
Yeah, in terms of MMV, I'm adding about the same amount as it comes with Quest, but there's probably a little bit higher. Like the one other thing I could calculate was legacy wellbores. Okay, so you could add a lot of that. You could add that into your costs, but it's I don't think it's a major cost. Like when I teach the course, let's say we're adding $1 to $2 dollars per megaton, US dollars per megaton in there. So it's not a big cost, but it's already in those economics. And so I kept them in there basically. But you can argue, oh, well, you got more legacy wellbores, so you got more to surveil, and fair enough. That's a decent question.
Thanks so much for the presentation. Nick Robbins from Darcy Partners. You struck on a great topic just around, I think, the right to win or the competitiveness from the perspective of an infrastructure player in the U.S. versus how are we going to look at this from individual, siloed, disparate teams from an EOR perspective in Canada, which I'm probably preaching to the choir here too. But would love to... Another point in that was around the systems thinking, where you talk about like the economies of scale and just the learning curve and everything from a first of a kind versus an nth of a kind build. And so I'd love to hear your perspectives, and if you could shed some light in terms of like that first of a kind versus nth of a kind cost advantage, and how this might look from the reference architecture and the cost architecture from Shell and Quest, right, versus how a smaller independent E&P, like if we translate that from like the multinational perspective to say like a Canadian independent or a private equity shop in the U.S.
The cost savings are, I think, pretty substantial. Okay, especially when you're talking about the EOR case, because remember, and I'm just roughly remembering this. So we put 440 million capital in, and so I basically re-drilled a lot of wells, and I also refitted everything. What you'd really do if let's say Weyburn, okay, so I was responsible for the design of Weyburn in 1990s, okay, and what you really have done there is you've replaced vertical wells with horizontal wells, and you've targeted a lot better, and it also drops your price. When it comes to technology, I think improvements in 4D seismic and some of that stuff will have both impacts on the EOR case and on CCS case. So I think I'm taking an as-is case, what's in front of me right now, technical readiness scale of 9 on it, and just running with that. And I think those economics are slightly too pessimistic. But if you look at studies, okay, I've had the advantage of teaching courses in CO2 economics and whatever, it's usually 5 to 7 years payout. So it's nothing, I can't get investors super excited about EOR and EOR only. Where I think the technology is going is remote sensing. So the geophysics, geomechanics is better understood, and also how CO2 tracks in the reservoir, whether it's a CO2 plume in an aquifer or a CO2 plume in an EOR. We're better and better at that, and remote sensing has a huge impact on that. So I'm keen, but I'm not like 25, 26 anymore. I don't have that, you know what I mean? I've been beaten up enough times in life to know it'll impact it, but I'll still think it's a long-range project. Bruce, I wanted a question from you.
Hi, Bruce Carey, Peters & Co. Richard, I have a question on the Alberta carbon trunk line and your thoughts on it going forward. Because it seemed to me that when Enhance started up at Clive, that was going to be the flagship, and they built it, and everybody else will come, to quote the baseball movie. Right. And I've gotten the sense, I haven't looked at it in a while, but on the EOR side, I'm not sure that the performance is matching the original expectations. And then second, I haven't seen anybody really jumping on board to sign up for that. Do you have a sense or any knowledge on, what other fields might be in the queue, or what have signed up, or whether they've even indicated an interest in, using that opportunity in their own fields?
Okay, now I got to give you an answer here, but I'm going to give you my constraints. Okay, I'm obviously sit in the annual general meeting, which is about 15 to 20 minutes each year for Enhanced, okay? And we kind of agree that we're not going to share too much information on the screen. But what I can say is if you look at my map of where are the target reservoirs, you have a good feel. Yeah, there's a lot in central Alberta, and then especially if you start looking at the central Alberta, even on the east side of thing, if you take Cold Lake a little bit further, there's quite a bit of oil target there. And then you're getting into that immiscible CO2, so it doesn't even necessarily mean my screen. I'm just kind of... I could talk for hours on what you said, but I'd be breaking I'd have Enhanced on my back by tomorrow.
Is it more rosy than gray?
Yeah, I think the thing that I will say this is Enhanced, I think, is about 18 years old now, okay? And what I guess what we didn't anticipate is when we started out, a lot of people didn't want to sell their field. So Clive was one of the few ones we could get into and get it. Now what happens is a lot of the money that is available for capital in Western Canada is going to the Montneys and the Duvernays as well as the Clearwaters, whatever. So you always have competitive streams here you have to consider. I think a lot of those reservoirs people have been acquiring or are using a little bit more. I don't know what the purchase price of them, and I purposely keep my distance with Enhance, and rightfully so. I don't want to know too much of what their strategy is, but I think we were disappointed by you have Murray, Edwards, you got all those guys, Ian, and all those guys in there, and that we would have liked better oil prices, we would have liked no shale revolution to compete against, and that's same thing. You see that in the CO2 for the U.S. is that it's hard to attract capital when you're second fiddle, right?
One quick other question on multilaterals in terms of CO2 EOR. Are you aware? I'm not up on Permian and how much or if any multilaterals have been used down there, but what do you see as the opportunity for 6, 10, 12 leg multilaterals use in CO2 CO2?
With individual control, so I can control.
No, sir. No, sir.
Well, that's more of a challenge. I think when you look at some parts in Texas, Steve Meltzer's conference, I have the paper, but I can't remember it off. If you looked at it, it wasn't Exxon. It was like somebody, Chevron or something, running horizontals. They basically, they had a pretty dramatic improvement, and we've seen that with solvent floods in Canada with horizontals, but it varies. It's going to have a different response in Swan Hills than it is in, you know, kind of stuff that you're dealing with, sandstone type reservoirs or whatever. So it's a bit of an unknown.
Hey, Richard. Eric with IFP here. In the map that you showed, you didn't really clarify it, but it's mostly light oil reservoirs, right?
Right, correct.
Where would you put the limit in terms of oil viscosity or API for the CO2 application? Because there is a lot of heavy oil as well in Western Canada, but CO2 is not really the right target for it.
Right. I think, if memory stands correctly, when back in EPIC we used 25-25-25 rule. So it was 2,500 feet depth, 25% recovery factor, and 25 API is what we used as. You know, to be honest, I think that CO2, I know you may not agree, but the CO2, immiscible CO2 is got some real, you know, interesting phenomena that it's definitely, we can't rule it out, right? And I wouldn't be surprised if somebody showed me 20 or 30 years from now that you have a lateral from Cold Lake down to more Lloydminster, Central, the Hardisty area, and that kind of stuff. Because I do think those are, as you know, they're great reservoirs. They're full of crappy oil, right? So, or 25, I shouldn't say crappy oil, but less favorable oil.
A couple more online questions. First of all, Martinez just says, excellent presentation. And David would like to know if you can comment on the relative miscibility of CO2 within the reservoir in comparison to LPG solvent for both medium conventional oil and conventional heavy oil.
Okay, so basically, when you look at LPG, okay, it's really how much propanes, butanes, ethanes you're in. So it's kind of a hard correlation to say. If you're looking at just straight ethane, I better be right on this one. CO2 is better than straight ethane, but it's when you start adding more propane and butane into your mixture, like they did at Redwater and that kind of stuff, then it the miscibility can go into that lower range. So LPGs will do better with a near miscible condition for CO2, especially if you're adding propanes and butanes into that, enrich the mixture, right?
Thank you. And one more from Lewis, who is curious if you've tried any other types of gas versus carbon dioxide to improve EOR extraction.
Oh yeah, there was stuff that I had to throw out. Like, you can ask Roger. When he asked me the first time, I was like a scatterbrain idiot. Maybe I still am, but I had all these cases, and I had a comparison in there between vertical miscible floods and miscible floods in Canada. We've had a lot of success in those things. People don't necessarily, not everyone is success. Some have had problems, pushback, Swan Hills, Judy Creek. Some of those other ones have had problems because of the complexity of the reservoir. Okay, but when you look at it overall, we've had Lake and you add the Nisku reservoirs into it, we've had a very, 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 like world-class recovery factors in terms of reserves with hydrocarbon miscible. That's why I'm pretty bullish on Alberta, because I still think a lot of them, the timing wasn't right economically, for sure, to think about CO2, but the timing is right now. So, well, I think it will be. Give me a lateral, 100 kilometers, I'll take it from there. Sorry.
Yeah, I've got a question. So based on the rate of returns that you talked about, if you're sitting there as an oil executive, what I'm hearing you say is that the Clearwater, the Montney, all of the existing big plays that are going on right now have a much better rate of return. So then who would this appeal to? So if you're in that 7-year range, who would be in that game?
What I see as analogy in the States, it's infrastructure who have bits and pieces of the infrastructure in place, okay, especially pipelines. And then I also think it's going to be bigger companies. You're going to have to capture that tax benefit, right, associated with it. So it's not out of the realm for oil sands or those kind of things. For smaller companies, you're going to have to pick and choose, okay, where you go. Similar like what Enhanced is you know, we knew we weren't going to bring all the CO2 from Fort McMurray through.
So would it be, because the economics that you looked at, you weren't separating out who's making the money on the oil, who's making the money on the tax credit,
Right.
who's investing the capital? You said it was all under one umbrella.
Yeah.
So the only people that could possibly do something like that and structure it from a business perspective are probably the Enbridges, TransCanadas, Wolf Midstreams, like all these guys that are trading steel for coupons, like basically dividend payers.
Yeah, mainly that's true, except I would argue that even if you looked at laterals of Wolf and Enhanced and all that kind of stuff, is anything that's near an existing has really favorable economics, even if it's a small company, right? Because it's the cost of the pipeline and then the cost of the CO2 going into that in your thing. So if I'm looking at it from a small oil company point of view, I would say, well, look to where your pipelines are. You've got obviously surplus capability with Enhanced. That's not, or sorry, Wolf Midstream. So that's not any rocket science associated with it, but it's what you can get from that and how you can develop it from a small oil company perspective. And that's what you see in West Texas is the reason we're at over 3 billion barrels in place isn't because just there was Watts and Shell and Amoco and Exxon and whatever had the original. It's the spin-off business that comes off the tube in London.
Okay. Eric?
These poor people were torturing them. Okay.
Yeah, staying on the small company perspective, because you look at a really big project here. You're talking about 1.3 billion barrels. $1.3 billion. But how do you see the same thing if you're a small independent? You know, you want to do, because I can do polymer in a small field. What's the scale for CO2? I guess the problem is always the CO2 sourcing, but you can inject CO2 in a small reservoir and make a lot of money as well.
Yeah, exactly. Like, okay, I'm 68 right now. I'm not going to start another oil company, so Enhanced can stop worrying, okay? But at the same time, when you look at it, there's a lot of, you're in that near miscible range or you're in the CO2 range, and especially if you have sour service wells, okay? So a lot of your cost is your conversion to high pressure, and if you're already sour service, if you already have H2S in the system, those type of fields are very attractive in terms to develop. And the nice thing about them is they have a lot of data, okay? So you have lots and lots of old vintage wells, which is usually used as an excuse why you don't do it. But to me, it's way better to have the devil that you know than the devil that you don't. And I know I could have said that better. But so I look at a lot of CO2 projects, especially like Hardisty and areas like that. Or if I was 25 years younger, well, I would be looking at a little bit closer, considering, you know, assuming pathways, well, you know that Wolf Midstream's pipelines are where they are, right? And you've got some existing strategy. I don't know what more in Viking and stuff. I haven't looked in that central Alberta area or anything like that too much, but it's not all over. It's not just big companies. It's you've got to be clever with a small company. You got to be clever how to use the CO2. You're gonna have fracture channeling. Your early breakthrough is gonna occur, right? And so you have to be smarter, to be honest. Okay.
Thank you, Richard, for hosting today.
Okay.
And a great round of applause for Eric, Ali and Richard, and thank you everyone for coming. We have the space for another 30 minutes, so please stick around for networking. Thank you.